So today we're going to talk about experiment 6, which is the acid-catalyzed dehydration of an alcohol into its corresponding alkene products. You're going to start off using 2-methyl, 2-butanol, and you're going to use a little bit of acid catalyst, in this case sulfuric acid and water. So that's why I've got it written as H3O, but it is catalytic in acid. And you're going to get possibly 2 products. One, the first one, which we're going to call the Hoffman elimination product. You'll need to call your Hoffman and Zaitsev products in your textbook. And of course, the Zaitsev product plus water. Since it's a dehydration, we are removing water from this molecule to give the alkene or alkenes plus water. It is catalytic in acid, so we don't consume the acid during the reaction process. And so we regenerate it. We don't need a full equivalent of that. So let's talk a little bit about the mechanism of this particular reaction. And I'm going to simplify the acid into H plus and H2O just to make it easier to show the mechanism. So that's basically H3O plus. We've got a catalytic amount of it. And the entire mechanism for the formation of these alkenes through dehydration involves a series of acid-base reaction steps. So if you look at an alcohol, you'll notice that the oxygen of the alcohol functional group has lone pairs of electrons, making this a Lewis base. And if you also look at the number of carbons that we have for 2-methyl 2-butanol, we've got 5. So we've got 5 carbons for one hydrogen bond group, which means that this should be soluble in water, and in fact it is. So we can dissolve that in water with the acid around. And what happens is we get a simple acid-base reaction where the Lewis base reacts with the Lewis acid, showing our electrons as such. And that gives us a protonated alcohol with a lone pair of electrons left and a formal positive charge on oxygen. Okay? This is a reversible process. Okay, so it's an equilibrium. We can go to the right or we can come back to the left, and it's an equilibrium. However, once we have the protonated alcohol, that looks like water, and water is a pretty good leaving group. Oxygen being electronegative like it is, does not want to have that formal positive charge, so it's going to try to get electrons from a bond, and so what it does is it pulls those electrons from the carbon-oxygen bond completely onto oxygen, breaks that carbon-oxygen bond, and we end up generating a carbocation plus water. Okay, we've just dehydrated and we've gone through a carbocation intermediate. This step is known as the rate determining step of the reaction. And the reason is because, of course, generating a carbocation is a high energy thing to do. Carbon does not have an octet any longer, and so that's a very high energy species to obtain. Once we're at the carbocation stage, we can eliminate to get our alkenes in one of 2 ways. So I'm going to redraw the carbocation down here. And I'm going to just point out one of the hydrogens for right now. This is the alpha carbon. This is the beta carbon. And so this is what we call a beta hydrogen. And what we've got also in the mix, of course, is a lot of water. And water can function as a Lewis base. So now we've got a Lewis base in water. We've got a Lewis acid being our carbocation. If the water simply attacked the carbocation, you get back to your starting material. However, water can also abstract the hydrogen on the beta carbon. And the electrons from the carbon-hydrogen bond can go to the carbocation to generate our alkene. And of course, we regenerate H3O plus. So that's why it's catalytic. We start with H3O plus. We get H3O plus in the end. It's a catalytic process. Okay? As I mentioned earlier, the starting alcohol is soluble in water. However, the product alkene is not. And that's how we can drive, using Le Chatelier's principle, the equilibrium to go to products. All of these steps are technically reversible. However, once you get to this stage, this will separate from the water, and you're going to heat this up. This is also fairly volatile, and so it will distill out of the reaction mixture and be removed from the water and the acid. And so that drives the reaction towards alkene. And of course, this forms the Zaitsev product, which is the more stable of the possible alkenes. And we know that alkene stability drives this process. So in your experiment, you should observe the Zaitsev product being the major product. Okay? Now let's look at how we would form the Hoffman product. Notice there are more than one beta carbon on this carbocation. This, of course, being the alpha carbon, we can have a beta carbon here, but we also have a beta carbon here and here, these two being the same type of carbon. So we'll just pick one of them, and I'm going to expand it out so you can see what's going on a little bit, and I'm going to draw the hydrogens in. And it could happen that the water will actually abstract the hydrogen at this beta carbon. We'll call it beta prime. Okay? And then the electrons, just like before, from this carbon-hydrogen bond, can move into the carbocation, generating the Hoffman alkene as the alkene product. And again, of course, H3O plus to give us back our catalyst. And again, this is insoluble in water and volatile, and so it would distill out. And you will get a mixture of the Zaitsev and Hoffman products. But again, since this is the least substituted of the alkenes, it is the least stable, and you shouldn't form it in the greatest amount. And so you'll analyze this by GC in lab to determine the ratio of your Zaitsev and Hoffman products that you obtain. You're also going to be performing a bromine test which is a positive test for the presence of simple alkenes like what we're forming in this particular reaction. And the test is quite simple, very easy to do. You start off with your alkene. I'm just going to start off with the Zaitsev product that works equally well for the Hoffman product. And you will add that to a solution of bromine in dichloromethane solvent. And what you will get as a product is a dibromide, where what we've done is we've added Br2 across the double bond. Okay? And so this reaction is very facile, goes to completion very quickly. And the reason it's a bromine test is because bromine itself is kind of a reddish color. And so in the absence of any alkene, the bromine and methylene chloride should be a slight reddish color tint. We use a dilute solution, so it kind of looks like concentrated tea, really. And then when you add a couple of drops of your alkene, it will go to the dibromide shown here, which is colorless. And so if you add enough alkene to completely consume all the bromine, you go from a red solution to a colorless solution in this particular bromine test. And so that's a good test for the presence of alkenes, is to add just a little bit of bromine solution to it to see if you can turn it from a red color to a colorless solution. So we're going to go to the lab now, and we're going to do a demonstration showing you how the bromine test, what it is that you should be looking for, so you can actually see what the color changes and how distinct that's going to be. So as promised, we're back in the lab. We're going to show you a bromine test, but first I want to show you, this is a concentrated solution of bromine. You can see how red that is. It's almost a reddish brown. You can't really see through the liquid at all. You can also see there's some bromine vapor above the solution. So bromine's actually quite volatile and quite toxic actually in the concentrated state. And so we don't want you working with that directly. This is a solution of 1 drop of bromine in about 5 milliliters of methylene chloride. You can see that it's much lighter. You can actually see through it. However, it does still look kind of reddish brown, and I kind of think it looks like kind of a concentrated tea kind of appearance.
but nonetheless it is that reddish brown color, but it is transparent. You can see through it. And here, you probably can't see the liquid in there too easily. This is cyclohexene, which is just a pure alkane. You can also see that it's clear. And we're going to take a substantial amount of this and add to the diluted solution of bromine. We would never add this to the concentrated solution of bromine, given that the reaction is very exothermic and would probably overheat and boil away the hexane very energetically. So I'm going to carefully open up the cyclohexene and the diluted solution of bromine, and I'm going to take a little bit of the cyclohexene solution with my pipette, and I'll add a few squirts of that in there, and you can instantly see the disappearance of the color. So that's what you're going to see in the bromine test. You will see the starting dilute solution of bromine. I think what you all will be using in the lab is about a 2% solution, so it'll even be less intensely colored than what I was showing you for the purposes of the camera. But when you add your couple of drops of your alkene solution to the bromine solution, if you have an alkene, you should see the rapid disappearance of that color.